So this is a typical test question where you need to design a cylindrical container whose volume V is given, such that its surface area S is minimized. Okay? So again, think about this. The volume is fixed. It can be 1 cubic meter, it can be 10 cubic foot or something like that. But how we designed a cylinder like a drum, such that we minimize the surface area of the material. That's what you said before when I asked for examples, when we'll minimize a function. So let's write. So design a cylindrical container whose volume is V, such that its surface area S is minimized. Okay. So really, the two quantities that we know, or the one quantity we know, is V. When we design a container like that, a cylindrical, we need to know two things. We need to know its radius, and we need to know its height, right? Because this is what a cylindrical container is. So let's sketch a cylindrical container on the side and see what its surface area is made of. So how you make a cylindrical container? If you look at a piece of paper like this, a rectangular paper, and you roll it around to make a cylinder, like so, right? Here's a cylinder. You open it up, and the envelope is rectangular. On top of the envelope, you need to have a cover on top and a cover at the bottom. Those will be the bases of the cylinder. So, if you cut it wide open, or before you cut it, if you take a rectangular sheet like so, you fold it, then the height of the cylinder is also the height of the or the width of the rectangular. And then let's say this is R, the radius of the cylinder. And now we have on top, you have a circle with the radius R, and you have the same thing at the bottom. That's how you make a cylinder, okay? What about the length of this rectangle? Well, we know the width is h, the length is the circumference, which is 2 pi r. And the area here, let's call it a rectangle, like so, is the circumference times the height, so it will be 2 pi r h, right? And the area of the circle will be pi r squared. So we'll write here, area of the circle will be pi r squared, and same is the area of this circle. So the total surface area will be 2 times pi r squared plus the area of the cylinder, of the envelope or the rectangular, which is 2 pi r h. Okay, now the problem is we have two unknowns, r and h. So what else we can do to eliminate one unknown. What is it that we know about the cylinder that we haven't used yet? Okay, let me ask a different question, then related question. What is it that going into assignment, what is given to us? What is it that we know? I'm sorry? All we know is the volume is V. The volume is a certain, normally when you see a problem like that in a test, you'll be told the volume is 4,000 cubic feet or 5 cubic meters, something like that. That will be given to you. Or you need to come up with R and H that minimize the surface area. The volume is given. So what is given is the volume. Do you remember the volume of a cylinder?
Area of the circle times height.
Right. So it will be pi r squared times h. And this is given. So from here, we can extract the height, right? We can say that the height is V divided by pi r squared. And now this putting here will eliminate one unknown and will keep the target function with one variable only. So the target function now is equals 2 pi r squared plus 2 pi r, instead of h, we have v divided by pi r squared, like so. So we need to massage it a little bit, and we have 2 pi r squared, and let's see, pi and pi cancel out, and we have 2v divided by r if I see it correctly. This is the target function. Let's take it to the next page. And let's do it. Let's write, instead of 2v divided by r, let's write it r to the negative 1, because we love the power rule for differentiation. And now we'll take the derivative and we'll find critical numbers by setting the derivative to equal 0. Is anybody still need to have another look at the page 3, the page on the left? No, you're all good? Can I take it off the screen? Thanks. All right, so the derivative here is fairly simple proposition. 4 pi r minus, remember, v is a number, it's a fixed number, so minus 2 vr to the negative 2. And for critical number, we want it to equal 0. We can write it as 4 pi r minus 2v divided by r squared equals 0. Or if I want a common denominator, well, we have 4 pi r cubed minus 2v over r squared equals 0. Now, since r cannot equal 0, then I can ignore it and just equate the numerator. We can divide it also by 2, and you get 2 pi r cubed equals v, and therefore r equals the cube root of v divided by 2 pi. Okay? So this gives me the radius. And here we can put an example. If V equals 5,000 cubic feet, then you have a certain number. For example, if V equals, let's put 1,000 cubic feet, then we have R, the radius, will be the cube root of 1,000 divided by 2 pi, or this will be calculated as 5.42 feet, I think. You can check this out. Go ahead, JT.
What?
You said something.
Yeah.
Go ahead.
I said it took me a second to figure out how you jump from 4 pi r to the third minus 2b over r squared equals 0 to 2 pi r to the third.
Well, I said I ignore r. I said because r cannot equal 0, I multiply everything by r squared. So I'm equating only the numerator. And then I have a common factor 2, so I divide everything by 2. So, all right. Now, the thing is we need to find h as well. We are not out of the woods yet. So what is h? Well, h is, we had it as, in the previous page, V divided by pi r squared, right? So we need to work on this one. So V divided by pi r squared. So here we're going to have a little challenge. Okay, pi, and now I need to square this thing. Now, this is the same as saying the V divided by 2 pi to the power of 1/3. So if I square it, I have V divided by 2 pi to the power of 2/3. Okay? So if pi times V divided by 2 pi to the power of 2/3. You see that, folks? Really? Somebody yawned loudly. I'll do a little dirty trick here. Let's see how dirty I can get here. Okay? I want to have 2 pi. I want to have V divided by 2 pi also here. So what I'll do, I'll multiply and divide by 2. And you'll see why in a minute. And I have V over V divided by 2 pi to the 2/3. There is a pi here still. Okay, do you see that V over 2 pi? Yeah.
Why substitute in for r if we already know what r is?
Well, I want to derive an expression for h. If it was a numerical question, then once I find 5.42, I'll do it. But remember, this is a generic question. That there were what we call literal. All you have is V, and you want to come up with the expression for R and H. There is also an interesting result here. So if you bear with me, you'll see the result. So, but look at the math here. This is a little bit of algebra trick here. Okay, I'm going to write it as H equals to 2, and on top I have V divided by 2 pi, and at the bottom I have V divided by 2 pi to the 2/3. Okay, what happens if we divide exponent? This is V divided by 2 pi to the power of 1, and I'm dividing by the same thing raised to the power of 2/3. What we do normally in this case, we subtract the exponent. Remember that? So it will be 1 minus 2/3, like so. And at the end, we have 2 times v to the 2 pi raised to the power of 1/3, or 2 times the cube root of v to the 2 pi. Now, why the heck did I go through all this trouble? What is r? Almost. What is the difference between h and r? Wow. So, results.
So height is equal to diameter.
Very, very good. R equal the cube root 2 pi, and h equals 2r equals the diameter, as JD said. This is a very good observation. So this tells you how you design a drum. Think about it. It tells you that whatever you have for the diameter here, d, when you design for maximum efficiency, the height is the same as the diameter. Now, go ahead next time you travel on the road and go to an oil container farm. And normally you see it next to a port or big airport or harbor, and you're going to see the cylinders. Now, you probably don't see the full height because A, you are from a distance, B, there is a concrete fence for spillage container. But if you come closely, and if you can measure the part of the container that is buried in the ground, you'll see that the designer designed it like this. I'm talking about the big, big containers where the material, the cost of the material is significant. Okay? You'll see that they designed it such that the diameter and the height are equal to each other.